Good morning, everyone. Confirm that you can hear me. Good morning. Can you verify that you can hear me? Okay. All right. Thank you, Sky in 124. All right. So welcome to our second lecture on complex numbers, and we are going to continue with section 6.1, and then we will get into section 6.2. Right. So let's just recap what we did yesterday. So yesterday we introduced complex numbers, and we ended up with a standard form. So we started off with Z being an ordered pair, and then we ended up with this form, which is called the standard form. Z is equal to A plus BI, where A is A and B are real numbers, and the real part of the complex number is A, and the imaginary part is B. And here, let's just say this is not equal to BI. You don't include the I when you write the imaginary part. And then we also know that I squared is equal to 1, or I is the square root of minus 1. And then we've got two operations. One is addition, and then the other one is multiplication. And we know how to do this. We saw how to do the multiplication. And then we had a theorem which said, also the question that we asked was, can we divide two complex numbers? And the answer was yes, if it's non-zero. So theorem 6.1.10 tells us that if you've got a non-zero complex number, then there exists a unique complex number W such that Z times W is equal to 1, and that is the inverse of Z, right? And the question that follows then is, so we proved that it exists, this unique W, but how do we find W, right? So in other words, how do we find the inverse of a complex number? And that is going to be what we are going to talk about, I think, for the rest of the section 6.1 before we get into 6.2. So before we do that, we need to define what is called a conjugate of a complex number, and that's what we are going to look at now, for us to be able to find the inverse of the matrix. Sorry, not matrix, complex number. So what is the conjugate of a complex number? So if you've got a complex number, Z is equal to A plus BI, then its conjugate is the complex number, which is denoted by Z bar, right? So that's important there. Z bar represents the conjugate, and the complex number is A minus BI, right? So here we've got a plus, there we've got a minus. That's the only difference, right? So Z bar is not equal to minus Z, right? Please note that we are saying you're just changing the sign on the imaginary part of the complex number. That's where you're changing from positive to negative, or from negative to positive. Right. So let's look at some examples of conjugate numbers, conjugate complex numbers before we get into the inverse of a complex number. So if you've got a complex number 2 minus 3i, then by the definition that we have there, the conjugate of that complex number would be 2 minus 3i, which becomes 2 plus 3i, right? And then if you've got 3 plus 2i, then the conjugate would be 3 minus 2i. And then we are going to draw these or put them on in a Gantt diagram to see how they the geometric interpretation of a conjugate of a complex number. And then we've got 2i, the complex number 2i, and that is going to be equal to 0 plus 2i, right? Which is going to be equal to 0 minus 2i, which is minus 2i. Here I'm just illustrating. Otherwise, you don't have to do all the steps there. And then the last one is 4. So the conjugate of the complex number 4 would be, for us to really see what the complex number is, we can just add plus 0i there. And that would be 4 minus 0i, which is equal to 4. So in other words, the complex number of a real number is just that number, right? So that is the conjugate there. Let's put these on in a Gantt diagram. So 2 minus 3i. So the real part of that complex number is 2, and then we've got minus 3i. So this would be 2 minus 3i there on this point. And then if we were to put 2 plus 3i on the Gantt diagram, then we've got 2 here and then plus 3i. So you can see that we have just reflected about the real axis, right? We just reflected this this point using this as our mirror, the real axis, right? So we get that. And then if we put 3 plus 2i, then we've got the real part is 3, and then the imaginary part is there. And then if we want 3 minus 2i, it will be somewhere here, right? So you can see again that we had to just reflect. And if we look at 2i, then 2i would be here, right? This would be our 2i because the real part is 0, so we would have said 0 here and then 2 there. So we get our 2i there. If we reflect, we are going to get it to be here, which is minus 2i there, right? That will be our complex number there. And then for 4, so 4 is a real number, so we are here. If we reflect 4 here, so it's on the real axis. So if we reflect it about the real axis, it will still be on the real axis because you are on the mirror, so it will not change. So as expected, we see that the conjugate of the complex number 4 is also 4, right? So that's the geometrical interpretation of that. Right, let's look at some properties of conjugate complex numbers in relation to the complex numbers. So this is theorem 6.1.12. By the way, if you have questions, just post them. I'll be checking the chat. So the theorem says, let Z and W be complex numbers. Then the following statements are true. So it says the conjugate of the sum of those complex numbers is going to be the sum of the conjugates of those complex numbers. That's the first one here, right? So we can see that you can sort of divide this bar and put it separately like that. And then the next thing is this also applies to multiplication. The conjugate of the product is equal to the product of the conjugates, right? So we've got that statement over there. And then the other thing is that if you multiply z by its conjugate, then you get a real number. And in fact, the real number is known. It is going to be the real part squared plus the imaginary part squared, right? So if z is equal to a plus bi, then z times z bar would be equal to a squared plus b squared. And this should be something that is sort of familiar. If you look at z is going to be, if we want to find the modulus of z, we say this is the square root of a squared plus b squared. So in other words, this is going to be equal to, so if you square this, you're going to get a squared plus b squared. So in other words, this is equal to that just by using what we have there. And I think this is a property that we are going to have in one of the theorems, if I'm not mistaken. Right, so this is the property that we have here. And the last one is that z bar bar, so in other words, the conjugate of z is equal to z. So if you think in terms of matrices, just to relate it to what we already know, we know that the inverse of an inverse is going to be equal to a, right? And if you do this even for numbers, 1 over a, so 1 over a is equal to a, right? So that's sort of what we are saying here. They also have this property on conjugates of complex numbers. Right, so the proof for the most part will be left as an exercise. We'll just do one of them, and we are going to do 2, which is that one. Sorry about that. Which is that one, right? So we want to prove that if I've got this, this is just going to be equal to that. And the proof is quite routine. So let z be equal to a plus bi, and w be equal to c plus di, right? Where we know that, of course, a, b, c, and d are real numbers. And from here, we want to show basically that if we take this, we find what the expression is, and then we take that, we find another expression. If the two expressions are the same, so that would mean that this is true for any arbitrary complex numbers that you pick, right? Right, so we say, well, for us to calculate the first one, we have to find what is ZW equal to. So Z dot W is going to be equal to AC minus BD. This is just using the formula there. Just the multiplication of two complex numbers. And so this would be what we have. So if we say the conjugate of that, we are just saying the conjugate of what we have here, AC minus BD plus AD plus BC I with that on top. And we know by definition that this is going to be AC minus BD, and then we just change the sign on the imaginary part, so we get minus AD plus BC I, and that is what we get. So if we call this 1, let's now look at the other side. So this was the left-hand side of our statement here. Let's look at the right-hand side. So the left-hand side is that. The right-hand side, I meant to say the left-hand side is this one, right? So the right-hand side is going to be Z bar times W bar, so the conjugates there. And what is this? This is A plus BI, so the conjugate of that, plus times the conjugate of C plus DI, which we write like that, right? And then we say, what is the conjugate of Z? It's A minus BI, right? And then what is the conjugate of W? Is going to be C minus DI, right? And then from there we can then do the expansion there. So AC minus ADI minus BCI minus or plus, because we would minus minus, so plus BDI squared, right? And then if we change this to a minus 1, we know that I squared is equal to minus 1, so we can say AC minus BD, right? That is our real part, and then the imaginary part is going to be A AD plus BC, right? I, because if we take out the minus, right, we factor out the minus, we get that. And if we call this 2, then we can see that if I look at 1 and 2, they are pretty much the same. So 1 is equal to 2. And since Z and W were arbitrary complex numbers that we picked, it means therefore the right-hand side is equal to the left-hand side. Right, so our statement is true. Right, so you can go and look at the other statements in this theorem in sort of similar fashion. You just say let Z and W be equal to some complex numbers, and then you just do a direct calculation. I'm sure it will come out. Right. Now that we've got all these nice properties, we are in a position to find the inverse of a complex number. And this is theorem 6.1.13, which says let Z be a non-zero complex number. So as usual, we want non-zero complex numbers, otherwise we are not going to be able to divide by 0, right? Then the inverse of Z, which we are going to denote by Z to the minus 1, is equal to 1 over this real number. So that real number is 1 over Z times the conjugate of Z times the conjugate of Z, right? So this, if you remember in theorem 6.1.12, that we say this is a real number, right? And in fact, we know what the real number is. So here, if you look at the first part there, it's just a real number. And then the second part is what is a complex number. So what it's saying is the inverse of Z is a multiple of it's a multiple of the conjugate of Z. That's what the theorem is saying here. So let's look at the proof of this theorem. The proof is quite easy. So what we want is to find some complex number. So we know that the inverse is going to be unique. So if we only find some complex number W such that this is equal to 1, then we are able to then say, well, that is the unique inverse of Z, right? So to prove it, we just need to check if this Z inverse that we have proposed actually satisfies this. Once it satisfies this, then we are happy, right? So what do we say? We say, well, we just need to multiply Z by whatever we have proposed to be its inverse, and then we check if it's going to give us what we want. And that is going to be equal to 1 over Z bar times Z bar, which if you look closely, this is just Z bar. So Z times Z bar on top, and then Z times Z bar on the bottom. And because this is non-zero, we know we don't have a problem on the bottom there. So we then see that that is just equal to 1. And so because it satisfies that, we can claim that this is the inverse of Z as claimed in the theorem. So that is the proof there. Right. So now we have an idea of how to find the inverse of a matrix, of a complex number, sorry. And so now what we want to know is how can we divide? Well, division is such that if you've got Z and W and you want to divide Z with W, where W is a non-zero complex number, then Z over W will just be Z times the inverse of W. Since now we know what is the inverse, we can find what this is going to be equal to. So that's how we divide our complex numbers. Now let's look at it from a practical point of view. And here we're going to look at this example. So we want to find the complex number 1 plus 2i over 2 plus 3i. So in other words, we're dividing this with that, and then we want the answer to be in standard form, right? So what do we do? So we say 1 plus 2i over 2 plus 3i. Well, if I've got this, I can multiply by something and divide by that something again, and this doesn't affect anything, right? So this is still equal to what we started off with. And notice that we are putting what we have put here is actually the conjugate of the denominator, right? Because once we do that, at the bottom from this statement, we are going to know that if we put this, then we are going to get some real number at the bottom. That's the idea there. So here we know that when we multiply this with its conjugate, we are going to get some real number. So we then say this is going to be equal to, so at the top, if you expand there, we get 2 minus 3i plus 4i and then plus 6. So if we say 2i times minus 3i, we get minus 6i squared, but I squared is minus 1, so we then end up with a 6. So we get that. And then at the bottom, we are going to get the real part squared times the plus the imaginary part squared. So we get 2 squared plus 3 squared, like that. And then from there, we then say it's a matter of now simplification. So if I take my real numbers on the denominator there, I get 2 plus 6, which is 8. And then at the for the imaginary part, we say minus 3i plus 4i, we get plus I, right? And then at the bottom, we've got 2 squared plus 3 squared, so 4 plus 9, we get 13. So we get our 13 there. And then to write it in standard form, since the question specifically wants it in standard form, we then say this is 8 over 13. So that's the real part, plus I over 13, or 1 over 13i, whichever you prefer. That is what we have. And so that will be how we divide. So take note that this is what we need to do when we are dividing. And that is it for section 6.1. Now we get into section 6.2, which is on the modulus of a complex number. So before we do that, maybe just something to note that you saw that when we started, we motivated by saying that the complex numbers gives us solutions to some quadratic equations. In fact, it will go further than just quadratic equations. But actually, it turns out that they've got many uses in maths and applied maths and engineering, and some of the uses I've written here. So complex numbers have uses in many scientific areas, including vibration analysis, signal processing, electromagnetism, control theory, quantum mechanics, and fluid dynamics. And this is not an exhaustive list. You can go and find out more if you are interested to know what what are some of the uses of complex numbers. Right, so let's get on to section 6.2. So we know that R is a real line, and we sort of saw that for complex numbers we can't represent them on a real line, so we need something different, which is the complex plane. And if you've got a complex number z, which is a plus bi, then if you want to plot it on the complex plane, then you take the real part on there, and then the imaginary part there. So you've got your a and your b, and then your vector will be somewhere there. So that will be z. And then if you want the conjugate, we know that this is going to be the complex conjugate, because we just reflect about the real axis, and then we get the conjugate there, right? Now let's look at what is called the modulus of a complex number. So we are trying to measure how big the complex number is, sort of, right? So what do we say? So the modulus of a complex number, z, which is equal to a plus bi, is the real number. I think I might have said something about this. So it's going to be the modulus. So we represent it by those two bars. So if you think about absolute value of a real number, that's what we are using here. Is going to be equal to the square root of a squared plus b squared. And what we are actually talking about is, so if you've got that complex number and then it's somewhere there, right? Then what we are talking about is this distance. And this distance is just, so this would be, if you think about this as a triangle, then this would be A, this would be B. And then if you want to find the distance for that, you then use Pythagoras theorem to find this modulus that we are talking about. So that's pretty much it. So that's the modulus there. And then example here, the modulus of 2 minus 5i is going to be equal to the square root of 2 squared plus minus 5 squared, which is 25 plus 4, which is then 29. So the square root of 29 there. So you can go and look at some of the questions in the exercises to familiarize yourself with this, but that's pretty much it. And then, so remember that we've got complex numbers are an extension of real numbers. So what we want to check is, do we still get the same result if you're dealing with a real number? So is the definition of the modulus of a complex number consistent with what we already know, which is the absolute value of a real number? So it turns out it is consistent. So if z is equal to a plus bi is real, right? That is, if b, the imaginary part, is 0, then the modulus of z is equal to the absolute value of z. So if you've got a real number there, a, then it's going to be a plus 0i. And then if we use what we have here, it's going to be the square root of a squared, right? From the definition that we have on top there. And that becomes a if a is greater than 0, and minus a if a is less than 0, which is just the definition of the absolute value of a real number. So that's what we are saying there. Right, now let's look at properties of modulus of a complex number, and we'll then combine all the ideas that we have. So so we've got theorem 6.2.3, which says let z and w be two complex numbers. then the following statements are going to be true. The modulus is going to be greater or equal to 0, right? And z is the modulus of z is going to only be equal to 0 if and only if z is equal to 0. So this is sort of like a, if you think about the property, the absolute value of a real number, right? That's the property there. So it's extended to complex numbers by this statement. All right. One other thing to note is that the real part of z is always less than or equal to the modulus of z, and this same applies to the imaginary part. It's going to be less than the modulus of that. Right. And then the next property is that I think this is what I talked about. I talked about it prematurely there because we hadn't defined the modulus of z. So basically, the modulus of z squared is going to be equal to z times its conjugate, right? And I sort of did the proof there. So if you just remember the definition of the modulus of z, and then you can then apply what we have in that previous theorem to get this statement. And then the third property, the fourth one is that if you've got the modulus of ZW, you can sort of divide. So if you think about real numbers, we know that AB is going to be equal to the absolute value of A times the absolute value of B, where A and B are real numbers, right? So this is an extension of that. And then it turns out that in the fifth property there, that the modulus of the conjugate is the same as the modulus of Z, right? You can sort of see why, because when we take the modulus of Z, we square all the real part and the imaginary part, so that doesn't change anything for the conjugate and the complex number. And then if you've got a non-zero complex number, then the modulus of the inverse is equal to 1 over the modulus of W. So we get this nice property here. And some of these we'll see them into play when we are looking at more work on complex numbers as we go further. And then if again, if you've got a non-zero complex number, then the modulus of z over w is going to be just the modulus of z over the modulus of w, right? And then lastly, we've got number 8, which is the modulus of z plus w is going to be less than or equal to the modulus of z plus the modulus of w, and this is familiar. So this is the triangle inequality for complex numbers. And all the other statements we are going to have, they'll be left as an exercise, but we are going to prove this last one, which is the triangle inequality for complex numbers. So let's see what we have. So again, we sort of use the same strategy that we used for vectors. And so we are going to take the square of this, and then we will start from there, and then we can use the fact that the modulus is monotonous, and then we can then conclude our statement. So we start off with this, but we know from the statement that we have in 3 there, so we know that if you square the modulus of that, then you get that times its conjugate, and that is coming from property number 3 there. So you can put the property here, number 3. And then from there, we then say this is going to be equal to Z plus W. Now we want to deal with the bar. So we say this is going to that by that. And this is a statement in theorem 6.1.12, I think. We know that we can do this. And then we then do our expansion. So we get Z times Z bar plus Z times W bar plus W times Z bar plus W times W bar, right? So we just expand it there. And then we know that this is going to be equal to that by the same statement that we have there. And then we've got Z W bar WZ bar plus the modulus of W squared. Again, we are using the property 3 in this theorem. So theorem 6.2.3, number 3, right? And then from here, there is a property that you is given as an exercise. So it's exercise 6.1, number 3, which says Z plus ZW, sorry, Z plus Z bar. So Z plus its conjugate is equal to 2 times the real part of Z. And it's really not that difficult to prove. So this means that, so we want to use this idea here to deal with that. So we are saying Z plus Z bar is that. So we want to check if I take this and do the conjugate, do I get this? If I get that, then it means that I've got this scenario, right? So if I do this, then I get this is going to be equal to Z times W bar, because if I think about this, so what we maybe let me just do it in full. So we've got Z bar bar times W, sorry, not Z bar bar, but Z bar times W bar bar, right? That's what we do here. And then we've got W bar bar, which is the conjugate of W, becomes the conjugate of Z times W. So we get that. And once we get this, we know that this is going to be equal to W times Z bar, this commutativity of multiplication of complex numbers. So in other words, this plus its conjugate is what we have in between here. So we can use this idea to then say this is equal to Z, the modulus of Z squared plus 2 times the real part of ZW bar, right? Plus the modulus of W squared, like that. And we know that this is going to be less than or equal to the modulus of Z squared plus 2 times the modulus of Z times the modulus of W plus the modulus of W squared. Again, here we are using this, we say the real part is always less than the modulus of Z. So that's what we used here to say the real part of that is less than the modulus of ZW bar, but this is just equal to like that. That's what we used to get that. And then from here, we then say, well, this is going to be equal to the modulus of Z squared plus 2 times the modulus of Z times the modulus of W. So we know that the modulus of W bar is equal to the modulus of W. That's another property that we have in one of the theorems, if not here, maybe the previous theorem there. And then, so we get that this is going to be equal to that. And then once we get this, then we've got what we wanted, which is to have that if we factorize that, we get that. And so therefore, what we have proved is the modulus of Z plus W is less than or equal to the modulus of Z plus, so this is squared there, W squared there, sorry, like that, right? That's what we have proved so far. And then if we take the square root from both sides, the square root of that squared is less than the modulus, the square root of the modulus of Z plus the modulus of w squared, and we get that z plus w is less than that. So the sign doesn't change here, because when we are dealing with these moduli, we know that all of them are greater or equal to 0, and we have said this this is coming from 1. So we know that we are not violating anything. So therefore we get that is that. You can put in all the details I'm saying, but yeah, that's pretty much it. So therefore we get our statement, which is what we wanted to prove. And that is that. Right. Do we have any questions? So if you're writing the proof, then you have to put all the details I was saying, but otherwise, this is the idea of the proof here. Do you have any questions? Okay, if you have questions, you can post in the chat. Now I'm going to look at a question in one of the exercises in the textbook, and it says sketch E, and E is the set of all complex numbers Z. So here we're just trying to illustrate how you can sort of use what we know now to be able to figure out what this type of object looks like. So we want the set of all complex numbers such that the modulus of Z is less than or equal to 3, and the image of Z is going to be greater or equal to 1. So that's the question we want to look at. And so let's break down what we have. So let's see what we know, that the modulus is less than or equal to 3, right? But what does this actually mean? Well, it means that you've got this scenario. So when you're looking at this type of questions, what you want is to figure out what happens when it is equal to, and then depending on the inequality there, either you're going to take the outer part or the inner part of whatever you have. So whenever you've got something like this, first figure out what when you've got something like this, first figure out what you have when it's equal to, and then from there we can then figure out what the region that we actually want. So in this case, we know that the modulus of Z is equal to 3. But what does that mean? So if Z is equal to A plus BI, which is pretty standard, then what we are saying is, so you say let Z be equal to A plus BI, where A, B are real numbers. And so from here, we know that what we are saying with this statement is the square root of A squared plus B squared is equal to 3. In other words, A squared plus B squared is equal to 9. And or you can just write it as 3 squared, right? So if you think of these as X and Y, you see that this is just a circle, right? With radius 3. So what we are saying is we've got a circle. This is just a sketch there. So this is the real part. This is the imaginary axis. And then we are saying we've got a circle there with radius 3. So this is 3 minus 3. 3 is not a very nice one here, but it gets the message across, right? So we've got this circle. So now we want where the modulus is less than or equal to 3. So in other words, we want everything that is inside this circle, right? That's the first condition. For us to satisfy the first condition, we want what is in there. Now let's look at the second one. Let me use a different pen. So for the image of Z to be greater or equal to 1, sorry, not the image, the imaginary part of Z to be equal to 1, we just look at the imaginary axis. And so we are saying, suppose this is our 1. So if if the imaginary part again is equal to 1, what we are talking about is this line, right? These are the points where the imaginary part of z is going to be equal to 1. These are the, basically what it's saying is we want complex numbers of the form a plus 1i, right? So a can be anything. So we can, if you think about the real axis, it can be anything, but the only condition is that the imaginary part should be equal to 1. So in other words, points on this line are the ones that are satisfying that. So in other words, what we have is that, and then we are told that the imaginary part should be greater or equal to 1. So we want it to be greater or equal to 1. So in other words, we are talking of all the points that are above this line that we have, right? That is the, those are the points that satisfy this property that we have over here. Now, to find out which ones are going to satisfy both, we just need to find points where we find all the shades, right? So we've got the blue shade and then the red shade. And so the points that we actually want are the ones that are here. And because there's this provision of either equal to, we have to include the boundary. And then, so we end up with something like something that looks like this. So this is 1 there, this is 3 there, and then this becomes the region that we want. And well, you can sort of draw the circle just to see what you had, but otherwise the region that we just want is the top part there. And that is 3, that is -3, that is -3. That's the real part, the real axis and the imaginary axis. And then there's a question. So we are not bounded by the 3 in the imaginary axis. When we are drawing so here I was just illustrating what this actually means. So in that case, we are not bounded. What then bounds us is, remember, we want to find these complex numbers that satisfy both. So when we get there, we want now the two areas that are common to both, because those are the only points that are going to satisfy the two conditions that we are given. And that's how we then get this part as the only region that satisfies both. So therefore, this is the sketch that we wanted for E. That is, so whatever is in there, including the boundary, is E. And that is that. I don't think I've got time to do maybe another example. Maybe let me see. So we're on 6.2. Let me just quickly look at another example in the textbook. So for example, number 2, okay, maybe let me attend to the question first. So can we then get the endpoints on the new region? I'm not sure what you mean, but basically the boundary is here. The boundary here is also part of the region that we want. So when you say endpoints, I assume these are the endpoints that you mean. Maybe you can just illustrate or explain a bit further if this is not what you're asking about. Right. Maybe let me just do A quickly before we stop. So A is defined as Z complex such that the real part of Z is greater or equal to 1, right? So what it's saying is if I've got this is imaginary, and then this is real. So therefore, if I want the real part to be greater, I have to find out what is the real part equal to 1, right? So in other words, we are trying to find complex numbers of the form 1 plus bi, where b can be anything, right? So our 1 is here. So basically what we want is this would be the real part being equal to 1, right? But we want where the real part is greater or equal to 1. So we then have to include everything that is on this side, right? And we also include the line. Why? Because the line would be where it is equal to. So this would be a rough sketch of what this region A looks like. Um, so you're saying, okay, now I'm attending to the question. So the endpoints here. So the endpoints are on the line there, and then on this on the circle, right? From that part to that part. That's pretty much the endpoints that we have. They are part of the region E. And in this one, A is anything that is to the right of this line, including the line. And that is A. So you can go and do more of these questions and see how you will fare with them. Otherwise, this is it. Thank you for attending. If you have questions, please feel free to stay behind. I'll be here for a minute or so. Otherwise, enjoy the rest of your day. And all the best to those that are writing today their class test. Thank you. Okay, I will assume that there are no more questions. So thank you for attending. Enjoy the rest of your day. Bye.